Hi everyone, today we're looking at halogen displacement. So in the last lesson we studied halogens, the fact that they are in group 7, that they are all different colours and that they get less reactive down the group. Now all those things are really important for what we're doing today. So if you're not totally sure or you can't really remember what was covered in last lesson, have a look over your notes now before you go any further. But let's get started. We're starting on page 117, and there's this image at the top of the page where it's titled Halogen Displacement, and you can see the halogens there, the way they would be written in the periodic table in group 7, and we can see their states, and we can see that as we go down the group, the elements get less reactive. These halogens get less reactive. The last thing you can see in this image is that the halogens do not like to live alone in nature. So you've got like F2, Cl2, Br2. Hopefully you can remember the name of what that is, and you should know that it's a diatomic element. And this is another place where they could ask you what is a diatomic molecule or what does diatomic mean. So it's really important that you know diatomic is when two identical atoms are bonded together. Okay, so really important that you know that. But I want to focus on displacement today. We haven't really looked at displacement since year 9 science. And maybe some of you can remember it in terms of metals. And in year 9 science, we said that we had two things in the reaction. We had a compound and we had an element. And usually then it was a metal. And the more reactive metal would have displaced the less reactive metal in the compound. And that was the idea behind that learning. But for halogen displacement, we don't care about the metal. We're talking about the halogen. So what we need to remember is the most reactive halogen in the experiment will end up being in the compound. Now, if the most reactive halogen was in the compound to start off with, nothing will change. But say the compound had bromine in it and you reacted it with chlorine. Looking at this image, we can see that chlorine is more reactive than bromine. So we would end up then with a compound having chlorine in it instead of the bromine, and the bromine has been evicted and is now by itself. So we're going to look at a few examples that we have here in the table below to help us get our head around that. Now on this table, you can see at the top of the table, we've got fluorine solution, chlorine solution, bromine, and iodine solution. So these are your elements as such in this reaction. Down the side, we've got potassium fluoride solution, potassium chloride solution, potassium bromide solution, and then potassium iodide solution. So down the side is our compound, across the top is our element. And what we want to remember is this order of reactivity. So as we go down the group, the halogens get less reactive. So let's look at the first combination there. The first combination is fluorine solution and potassium fluoride. So this box here. Well, fluoride is fluorine, just in the compound. So if you react it with fluorine, will anything change? They're both the same element. So you're right, nothing will change. So we're going to put an X there, okay? We're going to now look below that, and we've got potassium chloride plus fluorine, okay? So potassium chloride plus fluorine, let's look over at our chart. Which one is more reactive? Well, fluorine is more reactive. So what it will do is it will displace chlorine. So we'll end up with potassium fluoride plus chlorine. So there will be a displacement reaction there. Potassium bromide plus fluorine. Well, bromine and fluorine are both here as shown. Fluorine is more reactive, so it will end up in the compound. So there will be a reaction to change things here. And then the last one, potassium iodide and fluorine. Iodine is less reactive than fluorine, so it's going to be booted out because fluorine wants to be in the compound. The more reactive element gets what it wants. And remember, all of them want to be in a compound because that means their atoms are stable. The outer shell is full. That's why they're doing that. Let's look at the next table then. Fluoride, potassium fluoride plus chlorine. So which one's more reactive? Fluorine's more reactive. So fluorine will stay where it is. It will stay in the compound. There'll be no reaction. Potassium chloride plus chlorine, well, it's the same thing. So nothing's going to happen. Potassium bromide then and chlorine. Look, bromine is less reactive than chlorine. So chlorine will end up in the compound. So there will be a displacement reaction. And then potassium iodide solution and chlorine. Iodine is less reactive than chlorine. Chlorine will end up in the compound, so there will be a reaction. Looking at the third column then, bromine solution and potassium fluoride. Okay, fluorine is more reactive than bromine, so it will end up in the compound. Seeing as it's already in the compound, there'll be no reaction. Potassium chloride plus bromine, again, chlorine is more reactive than bromine. It's already in the compound, so there'll be no reaction. Bromine has no power to push the chlorine out and replace it. Potassium bromide and bromine, look, we've got that problem again. It's the same thing, so there'll be no reaction. And then potassium iodide and bromine. This is the one case for bromine where it will have a reaction. Bromine is more reactive than iodine, so we'll end up in the compound. And there'll be a displacement, so we'll end up there with potassium bromide and iodine. And then the last column there with iodine solution. Well, look, iodine is less reactive than fluorine, chlorine, and bromine, and it can't displace itself. So there'll be no displacement reaction there at all. It's not reactive enough to evict another halogen and take its place. So it will end up as the element all the time. Here's a few important facts I want you to remember. So the first one is that halogen compounds are colourless as solutions. And we normally react these as solutions. We've got a bit more control of them then. So we usually start off with the halogen compound being a colourless solution if we were to try a displacement reaction. The second thing then is that halogen displacement always then uses the halogen compounds as solutions, as I've just said. So when you're looking at a displacement reaction and you're trying to identify the colour of the halogen compound, it will always be colourless because it will be in solution. Okay, so that's just stating what I've just said there. The starting halogen compound is always colourless. We're moving on to page 118 now, and we're looking at the equation at the top. And the equation is potassium iodide plus chlorine produces potassium chloride plus iodine. Now, we can see displacement here. Look, the compound has changed. Chlorine has displaced iodine because it is more reactive. So the chlorine ends up in the stable compound and the iodine ends up by itself. So the least reactive halogen always ends up alone at the end. Now think about what I've just said about the colour of the halogen compounds here in these reactions. Remember, I said we always use them in solution, and solutions for halogen compounds are always colourless. So we've got potassium iodide there we're starting with. What colour is potassium iodide? Very simply, it is colourless, a colourless solution. And there at the end, we've got another halogen compound, potassium chloride. Again, all halogen compounds are colourless, so it's also a colourless solution. Now, this is where the colours of our halogens matter. Okay, so imagine you start with colourless potassium iodide in a beaker. It's colourless in a beaker. But you decide to add chlorine solution to it. Chlorine, remember, is a yellow-green colour, and it's a green solution. So imagine you're adding that yellow-green solution to the potassium iodide. Just like diluting juice changes the colour of water, so this halogen will change the colour of the compound. So as you add the yellow-green solution, initially, you will see the colourless solution turn a pale yellow-green. But then the reaction will start here because chlorine is more reactive. So there's going to be a colour change because the halogens are all different colours. Now, the compound doesn't affect the colour because look at the compound produced. It's also colourless. So it won't have any impact in the colour. It will just allow the colour to show. So what will happen here is we'll go from having a colourless solution through a transition of yellow-green for a second, and then it will turn the colour of the iodine produced. And iodine, remember, when it's in solution, is a yellow-brown colour. So what we're really going to see quite easily is a colourless solution change to yellow-brown. Because again, the yellow-brown will control the colour in that beaker at the end. Okay, so it's as if you've taken a glass of water, you've added orange diluted juice to it, and suddenly it's changed to blackcurrant diluted juice. So your beaker's not colourless, your beaker's not orange, it actually is that red colour of the blackcurrant because displacement has taken place. Okay, those things are labelled for you slightly apart from the colour of chlorine and the colour of the potassium chloride. You can write a few notes around that if you want, and you can add in those extra colours there. But remember, when we're talking about halogen displacement, we mention the starting colour of the halogen compound, so it will always start as colourless, and then we state the end colour of the halogen because that's what we'll show. We kind of ignore the chlorine in this one because it's only there for a split second if you catch it. So we have a few bullet points to write just below that equation, and these are the 3 bullet points I want you to write in. So the first one says halogen displacement occurs when a more reactive halogen displaces a less reactive halogen from a solution of its ions. Second bullet point, chlorine is more reactive and so it displaces iodine from a solution of its ions. So this wee bit's relative to the equation above, you'll notice. And then the third bullet point, when chlorine is bubbled into a colourless solution of potassium iodide, iodine forms and the solution turns yellow-brown. Now I want you to pause this here and write those 3 bullet points in. So there's a few rules to remember about this then, and it's really about describing our colours. So remember I said in a displacement reaction, we always say that we start with a colourless solution, and then we always say that we end up with the solution being the colour of the halogen produced, that element by itself. So look at the 3 points below. It says, if chlorine forms during the reaction, the something solution will turn something. Well, we always start with a colourless solution. So the colourless solution will turn, and it's going to turn the colour of chlorine because chlorine's been formed. So it's going to turn green. Write that in. Then the second point, if bromine forms during the reaction, again, it's going to be colourless solution will turn orange. And then the last one, if iodine forms during the reaction, the colourless solution will turn brown, or you could say yellow-brown there would be more accurate. Okay, brown or yellow-brown is accepted there. So this is a kind of thing that you would say in an answer. When they ask you, what is the colour change in this displacement reaction? You will always say colourless too, and then the ending colour will be the colour of the element produced. And it will be the element dissolved in water. That's why it's not just identical. That's why chlorine's green here and not yellow-green. It's why bromine's orange and not red-brown. And it's why iodine is yellow-brown and not grey-black. If it was just pure iodine, remember, that is a solid. So this is iodine dissolved here. Okay, let's move on to the next page then once you get all this copied in. The next thing we're asked about then in exams is to explain the trends in Group 1 and Group 7. And it's really important to be able to do this because when we look at this then in Year 12 and when we look at it at A level, these are things that are going to come second nature to us. At the moment they'll seem a bit strange, but soon you'll be so confident that it'll just roll off your tongue and you'll have no problem. So we're looking at page 119. Up at the top of the page, there's a table. Let's have a look. You can see on page 119 that this table at the top has got 4 headings. It's got the group number, the most reactive element from that group, and the trend in reactivity. And then we've got to write down and learn the explanation that explains why that trend exists. So looking at Group 1, looking back a couple of lessons here, we see that the most reactive element in Group 1 is francium, or francium as some people call it. And then the trend in reactivity is that the reactivity increases as we go down Group 1. And we want to explain that in terms of their sizes. Okay, now don't look at the explanation yet, look at the picture. Okay, so looking at the picture, you can see lithium has got 2 shells, sodium has got 3 shells, and potassium has got 4 shells. Now look at how far that outer electron, which is coloured blue here, look at how far away it is from the nucleus. Hopefully you should notice that in lithium, it's much closer than as you go down the group to potassium. So what happens here is that as we go down group 1, the atoms get bigger. And that means that little outer electron, which is all alone, is further away from the nucleus each time. Hopefully remember that the nucleus has a positive charge overall. And so it's the nucleus that holds the electron in place. It holds it close. But the further away the electron is, the less force that nucleus has to hold it, the less influence it has over that electron, and so it could be more easily lost. It's not held as tightly. Okay? It's quite a sad story when you think about it. It's not held as close, and so it's more easily lost. And the reality is, when an electron from a metal is more easily lost, the more reactive that metal is, because once it loses that electron, it becomes stable. And remember, that transfer of electrons, giving them, taking them, that is reactions in their finest. Okay, so let's look at the explanation you have to write down here. So the size of the atom increases going down the group. The bigger the atom, the further the outer electron is from the nucleus. So it is held with less force. Therefore, the outer electron is more easily lost the bigger the atom is, i.e., it's more reactive. So as we go down the group, we increase the distance between the outer electron and the nucleus. The outer electron is held less tightly and more easily lost, meaning it reacts more easily. Make sure you write that explanation down now and that you learn it really well, because that's something that is asked about over and over again. Now, group 7 is the one we're really interested in today. So you can see in group 7, fluorine, which is at the top of the group, is the most reactive here. So the opposite to group 1. And the reactivity decreases down the group. And it's to do with the idea that for a metal to react, so a metal like group 1 to react, they've got to give away an electron. But for a non-metal to react, they're looking to attract more electrons in. So keep that in the back of your head as we go through this. Look at the picture. Again, as we go down the group, we can see the size of the atom increases. And the same idea here is that as we increase the size of the atom, that force of attraction from the nucleus decreases. So what that means here is these atoms are trying to attract new electrons in. So because fluorine's outer shell is very close to the nucleus, it's very good at attracting a new electron in. It's a bit like a strong magnet. When you've got something close to the magnet, it latches on very quickly. It's attracted very quickly. But look at bromine. There's 4 shells in between bromine, okay, and the outside world. So there's a lot in the way to kind of counteract this attraction. So bromine has less of a force of attraction to attract new electrons in. So it's like a magnet that's further away. So fluorine is a magnet that's right beside the metal. Bromine is a magnet you're maybe holding 5 centimeters away. So it's less powerful to attract. That's the problem here. So at the top of the group, they're very reactive because they've got a great power to react because the shell is close. Bromine, the shell is very far away, so they're not very good at attracting. Our explanation then that you have to write down and learn is the size of the atom increases going down the group. The bigger the atom, the more shells the atom has, so less force from the nucleus to attract extra electrons, i.e., it's less reactive. Now, this can be a tricky concept, and some people will panic that it's hard to get your head around, but don't worry. My advice is that you write this explanation down and you just learn it. If you don't fully understand it right now, that's okay. Sometimes it takes a while for us to understand concepts. I mean, I know that there's stuff that I learnt at GCSE that I didn't understand until I reached A level. And that's okay, that's learning. So don't worry, just write the explanation down and learn it off. And that's all I need you to do right now. Do you know what? You might find in a month's time it does make sense. You might find tomorrow it makes sense. Just let your learning happen at its pace. But for now, get the notes written down and learn the explanation, okay? The understanding will come in time. One thing I do hope you remember, and it's seeming to be drilled into your head right now, is why elements have the same chemical properties. So the question below the table says here, why do the halogens have similar chemical properties? I really hope you can answer this without me already. So why do the halogens have similar chemical properties? Remember, it's to do with those outer electrons. Your answer should be, if you don't know it already, they all have 7 electrons in their outer shell. Having the same number of electrons in their outer shell means they have similar chemical properties. So make sure you take a second here, pause the video, and write your answer in there. But remember, to have similar chemical properties, you must have the same number of outer electrons. Now we're looking at 2 reactions of the halogens, 2 very common reactions. And the first one is how you would test for chlorine gas. In a lot of experiments, chlorine is given off. Now, hopefully some of you already are aware what's the problem with chlorine gas. I'm not talking about chlorine in your swimming pools. I'm talking about the gas. So this was the gas that was maybe used in gas attacks, in chemical warfare. Are you getting the idea? It's toxic. Chemical gas, chlorine gas, is really, really toxic. So if it's being given off in a reaction, we need to know, and we need to be able to test for it, because we don't want to poison ourselves when we're just doing a lovely experiment. So let's look at what the test is for chlorine gas. It's a very simple test, actually. It's using pH paper, or litmus paper in this case. So what happens here is you can see the litmus paper on the left has been dampened, okay? So they put a little bit of water on it so it's just damp, because we must have it damp so that the chlorine can dissolve. Otherwise, it won't react with the litmus. So it dissolves in the water and then it reacts with the litmus. And look at what happens when it reacts with the litmus. It turns the litmus paper red and then it bleaches it. And that's a very special property of chlorine, is that it will bleach things. So it will bleach our litmus paper, and that's its test. So what we're going to write down here in how would you test for chlorine gas is chlorine causes damp litmus paper to turn red and then bleaches it. Pause now and write that in. The second experiment we're looking at is what would you observe when subliming iodine? Now, some of you might be familiar with what subliming or sublimation is. Some of you may not be familiar. It's something that was in the old spec, but they do tend to mention. So we've put it into your notes so that you are familiar with it, because I think it's very important to know about this. And I think it's such a lovely experiment that it's worth looking at. So sublimation is a change of state from solid directly to gas on heating. So if you heat the solid, it will skip the liquid phase. It won't melt. It will just change to a gas. And that happens with iodine. When you heat iodine, look, it changes from a grey-black solid to this lovely purple vapor or purple gas. It goes straight to the gaseous phase, and it's a lovely colour. So our observation here then is going to be when heated, grey-black iodine solid changes into a purple gas. So pause here and write that in. On page 120 then, you will see that we have put in an exam question. So we've put in a past paper question about the sublimation of iodine. You'll see that it says solid iodine undergoes a change of state known as sublimation. Explain what is meant by the term sublimation. Now, I have told you that just seconds ago, so make sure you write that in. That's 2 marks. Then you'll see part B is a 6-mark question, and it says the result of an experiment to demonstrate The sublimation of solid iodine in the laboratory is shown in the photograph below. Describe how you would safely carry out this experiment. And you've been given a picture to give you an idea there. And you can see what I'm pointing out here for you is that in the beaker at the bottom is the grey-black solid that you start off with. Something has happened to that beaker because the grey-black solid has clearly sublimed, because I can see a bit of vapor. I see a bit of discoloration in the beaker, so there must be a vapor there. So it is sublimed, the gas has risen up, and then it has become a solid again on the bottom of that evaporating dish. So I want you to be thinking, what has had to happen to the solid to cause it to sublime at the bottom? But what has happened at the top to cause it to now freeze? What is in that evaporating basin? Do this 6-mark question now. Write it in sentences, remember, because that's how you get your QWC, your quality of written communication. Okay, so sentences, write down what has happened. Describe how you would safely carry out this experiment. Refrain from saying things like, I would do this, then I would do that. Just do it like a method. Write it like a method, okay? Once you get that done, then what I want you to do, you'll see on page 121 is where you're to write that, okay? Then I want you to mark your answers, and you'll see on page 122 that there's the mark scheme. So refrain from using that at the start. Try this question, okay? Because you could get a question where you have to come up with a method in the exam. It might not be one that you just know from doing it. It might be one you're asked to make up. So try that and then mark it and see how you get on. You will see the answer for the first question there at the top of the page, okay? Then you will see for part B is indicative content. Those are the bullet points that you wanted to have hit in your answer, okay? You get 1 tick for each of those bullet points, okay? And you'll see there at the bottom it says maximum of 3 safety points must include use of a fume cupboard. So you can't have 4 safety points, you can only have 3, and one of them must mention a fume cupboard because the halogens are poisonous. Okay, now, if you hit 1 to 2 of the bullet points, you will get 2 marks. Even if you only hit 1 bullet point, you get 2 marks, so it's great. If you get 3 to 4 of the bullet points, you get 4 marks, and if you get 5 to 6 of the bullet points, you get 6 marks. So I always think these 6-mark questions are worth answering and worth practicing because it's very easy to bank up the marks here. So have a go at that and then mark it. And as they say in Looney Tunes, that's all, folks. What you need to do now at the end is I want you to upload your work then to this assignment as a PDF or as pictures on a Google Doc. These are really the only 2 formats that the iPad supports for me to be able to mark these properly for you. So either a PDF, remember using Notes, that Notes app on your iPhone or an iPad if you have it, or you could use Office Lens if you have an Android phone, or just take pictures and put them on the Google Doc. Any problems, let me know and I will try and get back to you as soon as possible, but hopefully this should be handy enough. Okay, all the best. I'll chat to you soon. I'm missing seeing your faces, but I'm hoping that you enjoyed the snow last weekend and maybe made a lovely snowman. What a weekend to have. Take care. Missing you all.